In this video, we're going to look at the first set of notes in topic 12, which is all about this idea of improper integrals. So we're going to, of course, define what an improper integral is, and then we're actually going to break up this topic into two different types. So type 1 improper integrals and type 2 improper integrals, and we're going to see how to evaluate both of those. So just as a motivation section here, so if we go back and look at all of the definite integrals that we've been calculating so far, we'll notice, if you just go back and look at them, that up until this point, when we consider those limits of integration a and b, they've been finite. So they've been constants that have not been negative or positive infinity. And in addition to that, all of the integrands that we've seen, and remember an integrand is the function we are integrating, these have been defined over the whole region of integration. So they've been defined over the interval from a to b if we're integrating from a to b. So a couple examples of this. So sine of x, our limits of integration here are finite, and sine of x is defined for all values of x between negative pi and pi, our integrand sine of x. The next example here, 3x squared times e to the x cubed. We saw this when we first introduced substitution, I think. Our limits of integration are finite, and our integrand, this function, is defined for all values of x between 0 and 1. Or something like this, integrating 1 over t with respect to t. Our limits of integration, e and e to the fourth, are both finite, and our integrand, 1 over t, is defined for all values of t between e and e over 4. So not only have we been dealing with cases where our limits of integration have been chosen to define a finite region, but also when we've been looking at the integrand or integrating a particular function, we haven't had to deal with any situations where the integrand was undefined at a certain place. But of course, as you might suspect by what we've been introducing here, we can consider integrals as a way to measure area when we've got one or both of our limits of integration being infinite, so positive or negative infinity, or when there's a point or points on our interval of integration where our integrand is undefined. So some examples of that, let's say we're integrating the function 1 over x. Notice that our upper limit of integration here is infinite, positive infinity. Or something like this, integrating e to the x, where both of our limits of integration are infinite, so from negative infinity to positive infinity. So those are both examples of this, but we can also have cases where our integrand function is undefined at a point or multiple points on our interval of integration. So in this last example, we can see that our limits of integration are both finite again, but if we think about that lower limit of integration, we are actually dealing with a case where our function, our integrand, is undefined there because we have 1 over x squared, and when x is 0, we get that 1 over 0 problem that we can't have. So what we're going to see in this set of notes are things like this, where either we're dealing with one or more infinite limits of integration, or we're dealing with an integrand that is undefined at a point or points on our region of integration. So let's start with a bit more of a formal definition here. When we're referring to an improper integral, we're talking about one that either has, like we saw above, an infinite limit of integration, at least one, or has an unbounded integrand, meaning that there's at least one point where the integrand is undefined on our region of integration. So this is how we're going to split this talk about improper integrals. We're going to first talk about infinite limits of integration. That's what we're going to call type 1 improper integrals. And then we're going to talk about integrals where we have this unbounded integrand. We're going to call those type 2 improper integrals. So we're not going to worry about type 2 right now. We're just going to focus on type 1. Then we'll switch and talk about type 2 and how to evaluate those. So of the two types of improper integrals, this is probably the more common one. The type 1 improper integral is your infinite interval, where, again, at least one of the limits of integration is infinite. And this can occur in three ways. You can have a case where your lower limit of integration is finite, but your upper limit of integration is infinite. You can have the case where your lower limit of integration is infinite, in which case it's going to be negative infinity, and you're integrating to a finite value. Let's call that b. This is an a. Or you can have the case where you're integrating from negative infinity to positive infinity. So we're just going to go through these and see the general approach. I'm going to call this type A, B, and C, just to make it easier to label what we're talking about as we go through these notes. Okay, so the first one here is this, where our upper limit of integration is the infinite piece. So talking about version A here. So here, our integral of interest is in the form where we're integrating f of x from a to positive infinity. If our function is continuous on this interval, we can define the improper integral of f over this region as actually a limit, an integral involving a limit. The way we do this is we start with this improper integral, and we actually define a brand new integral. We define this integral here, where we're integrating from the lower limit, the a, but instead of integrating to infinity, what we do is we replace the upper limit with some finite value r. And the reason we do that is because if this upper limit of integration is finite, then we're integrating over a finite region, which allows us to use the second part of the fundamental theorem of calculus. So integrating this is just like we were doing with the evaluation theorem back in topic 11. We know how to do that. And then the way we convert this back to a situation where that upper limit of integration is infinite is we take the limit. In other words, once we find this integral from a to r, then we take the limit as r goes to infinity. So it's like we're treating r as a variable. We're kind of treating it both as a constant and as a variable. We treat it as a constant in the sense that we're basically using it as a number when we do our integration. But when we take this limit, we're now treating r as a variable, where we're saying let this variable r, let this value go to positive infinity. And that will give us our resulting area. Now, sometimes these areas are finite, sometimes they're infinite, as we'll see. It depends on the integral, but that's the general idea. And visually, this is what we're doing. So if we're integrating from a to r, this piece here, let's say this is our lower limit of integration, what we do is we just define some finite value r. Let's say it looks like this piece right here. We integrate from a to r, which gives us this. And then what we do is we let r, as we can see by this limit, we let r go to positive infinity, meaning we're essentially taking this upper limit and we're just letting it go. So this graph is of f of x. And this is what we do for all of these integrals of this type. We essentially remove the infinite piece or pieces of our limit of integration. We replace it with a constant. Then, when we take our limit using the evaluation theorem, that's where we take the limit, let r go to infinity, and that will give us our actual area that we're interested in. Okay, so that's what happens when the limit of integration, the top limit of integration is infinite. What happens if we're integrating from negative infinity to a constant? It's the same idea. So here's version B. In a similar manner, suppose now we're integrating f of x from negative infinity to a. So now the infinite limit of integration is the lower one. But we treat this the same way. So we were like, okay, well, we're starting with this integral. We don't want to deal with infinity or negative infinity in our expression, in our integral, because we don't know how to deal with that. So we once again start by defining a new integral, specifically where our lower limit of integration is now this finite placeholder r. We compute this integral using the evaluation theorem, and then we take the limit as r goes to negative infinity of the resulting answer. Okay, so it's the same general idea, except now our constant, our a, is the upper limit of integration. And we're integrating from negative infinity to a. So don't want to deal with negative infinity. So what we do is we define some cutoff point here, r. We integrate from r to a. And then once we do that integration, we allow r to go to negative infinity. Now, just a note about some vocabulary that we're going to start hearing in this set of notes. In those two cases that we talked about above, case A and case B, if we do this whole process and our resulting limit exists and is finite, then what we say is we say that the improper integral converges. In other words, it's giving us some sort of finite area as the result. So the improper integral converges, or equivalently, the integral is convergent. If we do this whole process, we calculate this integral of this new integrand, and then we take the limit, and the limit does not exist or is not finite, then we say the integral diverges, or the integral is divergent. So in other words, we're not getting a finite area, we're getting an infinite area as our result. And the vocab, the wording we use for that is a diverging or a divergent integral. Okay, so we'll hear convergent, divergent, converges, diverges a couple times in this set of notes. So if you're looking for the definition of those, they're right here on page 3. So there's one other case that we can deal with here with these limits of integration that can be infinite, and that's our version C, where both of our limits of integration are infinite. So last version here, suppose our integral of interest is of the form the integral of f of x, where both of our limits of integration are infinite. So what we do in this case is we actually break our integral up into two integrals, specifically where one of them involves our lower limit of integration. So one of them is negative infinity to some constant a, and then the other one takes up where we left off, so goes from a to that upper limit of integration, positive infinity. And the reason we do this is because both of these are things we just talked about. This was version A from above, and this is version B from above. And we just talked about how to deal with both of these integrals. So essentially what we do is we break up our original integral into two. And these two are ones that we can evaluate as either a version A or a version B, because one of them is from negative infinity to a, the other is from a to infinity. So we can break up this sort of integral into those two pieces. Now, in terms of convergent or divergent integrals of this form, this original integral converges if and only if both of these pieces converge. So they both have to converge. Otherwise, if only one of them converges or neither of them converge, the improper integral, this original one, is divergent, or it diverges. So just as an example, let's say this is our picture of our function, and we're integrating from negative infinity to infinity. So this whole region, if this kept going and going off in both directions. And so what we do is we just pick a point. We pick an A somewhere on our region of integration, somewhere between negative infinity and infinity, so it can be anywhere. And we use that essentially to break up this integral, or this region, into integrating from negative infinity to a, so going from negative infinity until this point, and a to positive infinity. And again, the reason this works and the reason we can do this is because this breaks our area up into two pieces. Now, to explain this a little bit better, I'm just going to do this here just so that we don't have to break up our examples as we go forward. I'm actually going to go back to topic 10, and I'm going to go back to the 10.4 notes, specifically that very last page, where we talked about this very last property, property 5 of definite integrals. So this property tells us that if we're integrating a function from a to c, so we're looking for a region of integration from a to c, what we can do, if it makes things easier for whatever reason, is we can actually break up this integral into two by just picking a point, a value, let's call it b, somewhere between a and c. And then what we can do is we can integrate from a to b to get that region in purple there. And we can also integrate the region from b to c to get this area in orange. And if we sum those two areas, we get the area of the original region of integration, this whole big thing. And I think I mentioned back in the video for the 10.4 notes that this was going to come in handy when we talked about improper integrals. It does, as we just saw, because this is essentially what we're doing here. So this is our original integral. We want to break it into two, so we're picking some arbitrary point A in between negative infinity and positive infinity, and we're using that to break up this big integral into two manageable integrals. So that's where we see that property. So let's go ahead and do a couple examples here and just get some practice with how we approach these types of integration problems. So the first example on page 4 here is telling us to find the integral of e to the x from negative infinity to 2, or show that this integral diverges. So finding the integral means we're finding the finite area that it captures, so showing that it converges to something. Or if we can't show that it converges, that means it diverges. So we'll get some practice with that wording as we go. All right, so we can see that our lower limit of integration here is the one that is infinite. We are integrating from negative infinity to 2. So how are we going to work with this? Well, our original integral here is the integral from negative infinity to 2 of e to the x. So what I'm going to do is I'm going to leave myself a little bit of room here. I'm going to rewrite this integral, and I'm going to replace negative infinity with a placeholder. I'm going to call it r, and I'm going to treat r as if it's both a constant and a variable. So I'm going to treat it as a constant in the sense that it's going to be some finite quantity, but we're going to take the limit involving r here in just a second. So just think of it as a placeholder. Treat it as a number. We're integrating from r to 2 of e to the x dx. And what I'm eventually going to do is I'm eventually going to take the limit of this integral. And specifically, I'm going to take the limit as I let r go back to what I replaced it, or what it's replacing. So I'm going to let r go to negative infinity eventually. I'm not going to worry about the limit for a little while, but that's eventually what I want to calculate. Actually, I'm going to make this a little bit bigger. It's kind of squished. I didn't give myself enough room. So again, eventually, what I want to do is I want to take the limit of r, or of this integral, by letting r go back to the thing it's replacing. So I'm going to let it go to negative infinity. Okay, so we're going to do the limit last, so I'm going to keep writing that limit notation because we're not going to do that just yet. Just like we were doing back at the start of the course, we're going to leave that limit notation in until we actually take the limit. And I'm just going to worry about this integral. So I'm going to compute this integral now, or evaluate it. So e to the x, remember e to the x is one of those nice functions where its derivative is e to the x and its integral is e to the x. So the thing that gives e to the x as a derivative is just e to the x. So this is going to be the limit as r goes to negative infinity of e to the x, and we're going to evaluate the e to the x from r to 2. Okay, so I'm still not taking the limit yet. That's going to be the very last thing I do. So I'm going to leave that limit notation in there. Okay, now I'm going to evaluate e to the x from r to 2, which means I'm going to replace my x with my upper limit of integration first, so e squared minus e to the r. Now this is the point where I take my limit. So now that I've got this set up here, where I've evaluated my limit and I've basically plugged in my r as if it was a number, now I'm going to take the limit. I'm going to let r go to negative infinity. So what happens when I do that? Well, e squared, that doesn't have an r in it, so that stays as it is. E to the r, so I'm letting r go to negative infinity. So this is like e to the negative infinity if I were to plug in, quote unquote, my r value. Remember when we have a negative exponent that we can rewrite it as 1 over the base to the positive exponent. And the reason I'm doing that is because I think that makes it easier to see what happens as I let r go to negative infinity. If I let r, my exponent, go to negative infinity, I get e to the something that's going to the negative infinity, which I can rewrite as 1 over e going to positive infinity. So now my denominator is growing without bound. It's increasing without bound. So that means this fraction goes to 0, which means e to the r, my original expression of this, goes to 0. And so all I'm left with is e squared. And that's my integral. That's the integral, or that's the finite area defined by the integral of e to the x from negative infinity to 2. So I'm getting a finite value here. E squared is a finite value. So I'm going to write this as this integral converges to e squared, meaning that it does produce a finite area, even though my lower limit of integration is infinite. So that's the idea behind improper integrals of this type. We look and we notice where we have an infinite limit of integration. We replace that with a placeholder, usually called r, and then we take the limit of that integral as we let r go back to the value it's replacing, in this case, negative infinity. And we don't take that limit, we don't do that limit calculation until basically the very end when we've done our evaluation theorem setup to complete the integral calculation. Okay, let's do another one. So once again, we are looking at an integral, in this case, the integral from 1 over x from 1 to infinity, and we want to either find this integral, so find the finite value it produces, the finite area, or show that it diverges. So in this case, the thing that's making this an improper integral is that upper limit of integration. We're integrating from 1 to positive infinity, 1 over x. And so I'm going to do basically just like I did in the above example. I'm going to say, okay, well, that infinity is going to cause me problems. I don't want an infinite limit in my integral. So I'm going to replace my positive infinity with r. Which gives me an integral I can evaluate using the evaluation theorem. And once I've done that, I'm going to get rid of the r by letting it go in my limit calculation to the value it's replacing, or infinity is not a value, it's this idea of infinite unbounded growth, but I'm going to let r go back to that. So I'm going to let it go to positive infinity eventually. So I've replaced the infinity with the little placeholder r. So now let's evaluate the integral. So nothing with the limit yet. I'm going to leave that alone. I'm taking the integral of 1 over x. So I want to figure out what function gives me 1 over x as a derivative. Well, remember, when we differentiate the natural log of x, we get 1 over x. So the integral of 1 over x is going to be the natural log of x. But remember, we have sort of that funky way of writing this when we're doing the reverse. We actually want to write this as the natural log of the absolute value of x. And we're evaluating this from 1 to r. So not doing the limit just yet, so I'm going to keep writing that limit notation there for us. And I'm going to use the evaluation theorem to plug in things in their appropriate places. So the evaluation theorem tells me that I can evaluate this by taking the natural log of my upper limit of integration, the absolute value of my upper limit of integration, r, minus the natural log of the absolute value of my lower limit of integration, that's 1. So now let's take our limit and see what happens. The natural log of 1 doesn't have an r in it, but the natural log of 1 is just 0. So that's nice and easy to work with. What about the natural log of r? Or more specifically, the absolute value of r, but r is positive, so that doesn't really matter. So r is going to infinity. If we put r in a natural log function, it's going to slow down its growth, but it's not going to stop it or change its direction. So even though the natural log of a value is a lot smaller than the original value, if the input, if r keeps getting bigger and bigger and bigger, so is the natural log of r. And this thing actually is going to go to positive infinity because r is going to positive infinity. So I have something going to positive infinity minus 0, which means this thing is just going to go to positive infinity, this integral. Now this is telling us that there is an infinite area defined by this integral. The integral of 1 over x from 1 to infinity is actually an infinite area. And the terminology we use for that, when we get an infinite limit like this, whether it's positive or negative, that's when we say the integral diverges. So typically, not always, but typically the convention is if we have an integral that converges, we like to state what it converges to. So like I said up here, this integral converges to e squared. When we have an integral that diverges, we don't really care as much how or why it diverges, like does it go to positive infinity or negative infinity, or does the limit not exist? We usually just say that the integral diverges because there's not really anything super interesting about why it diverges or the value or the concept that is causing it to diverge. We usually just say it's diverging, whereas with a convergent integral, we like to say what it's converging to. That's usually the convention with these sorts of improper integrals. Let's do one more, and then we'll talk about a couple other quick things before we talk about type 2. Right, so let's look at this one. So here we're integrating x squared times e to the negative x cubed, and we're integrating from negative infinity to infinity. So we either want to find this integral or we want to show that it diverges. So this is one that looks maybe like it's going to take a little bit more work because we have two infinite limits of integration. So if we go back to how we introduced these types of integrals before, this was our version C, where both of our limits of integration are infinite. And so the technique we're going to use here is I'm going to split this into two integrals. One of the form from negative infinity to some constant, and the other from that constant to positive infinity. So I'm just going to break this into two. I'm going to say this is equivalent to the integral from negative infinity to, I'm going to originally just call it a here, of x squared times e to the negative x cubed, plus, now the key here is picking or making sure you use the same value for your lower limit of integration in the next one here. So this is going to be a, whatever a is, and we're integrating here from a to positive infinity. Okay, now the next thing I want to do is I don't want a variable there. I don't want an a. I want an actual quantity. I want an actual number. Now this is where you have a bit of liberty as far as what you put in there as your a. So this function, let's just pretend it looks like this. It doesn't, but let's pretend it does look like this. So this function is defined for values of x from negative infinity to positive infinity. And what we're doing here is we're breaking up this area into two pieces where the thing that breaks it is a, some point a. And all we need for a is we need it to be a value between negative infinity and infinity. It doesn't matter what a is. You can pick 0, you can pick 40, you can pick 12, you can pick negative 20. You just need to make sure that whatever you pick for a, you use it in both of these integrals. One where it's the upper limit of integration when you're integrating from negative infinity to a, and the other, you want it to be a to negative infinity, and those a's have to match. So I'm just going to pick a nice, easy value to work with. A really nice, easy value to work with for a is 1. So I'm just going to go ahead and use 1 as the point on this whole region where I'm splitting my area from negative infinity to that point, to 1, and from 1 to positive infinity. So I'm going to rewrite these one more time where I'm actually putting in a value for a. I'm going to put 1. Which means in my second integral, I'm going to want to integrate starting at 1 to positive infinity. So in other words, I have rewritten this integral as the sum of these two integrals. Now, initially, it looks like we're going to have to do a lot of work. It looks like I'm going to have to evaluate both of these integrals. But one thing that's sometimes nice about this form of improper integral, where we're integrating from negative infinity to positive infinity, is if we go back to when we first defined this, back on page 3, all we care about is whether or not that original integral converges, and if it does, what it converges to, or if it diverges. And the only way that this original integral can converge is if both of the pieces that we've split it into converge to the same thing. So they both have to converge, and they both have to converge to the same thing. Otherwise, the original integral diverges. So sometimes this actually cuts our work down a little bit, because if we're able to show that at least one of these integrals does not converge, then we can immediately ignore the other one and just say that the original function does not converge, it diverges. If we find one that converges, then of course we have to check the other one. So if this converges, then we should check this one as well. But if we start with one and we find it diverges, then we have all the information we need to show that the original integral diverges. And what I'm getting to with that is, rather than do both of these integral evaluations at once, what I like to do is I like to always start with just one of them and just play around with that. If it shows convergence, then I'll have to look at the other one. But if it diverges, then I've already got my answer about the original integral. Because if one of these two diverges, at least one of them, the original one does as well. So just to see if I can cut my work down a little bit, what I'm going to do is I'm just going to pick this first integral, and I'm going to look at this first. So I'm going to basically ignore the second integral for a second, and let's just take a look at this. And I'll write this in blue just to indicate that that's the integral we're looking at here. Okay, so we're integrating from negative infinity to 1 x squared times e to the negative x cubed. Now, this looks familiar. This looks like our first example, where my lower limit of integration is infinite, negative infinity. So I'm going to go ahead and replace that with an r. So instead of negative infinity to 1, I'm integrating from r to 1, x squared e to the negative x cubed. And eventually, I'm going to take the limit as r goes to whatever it replaces, in this case, negative infinity. So now, this integral is something I can evaluate. But if we consider that integrand, that looks a little bit rough. And this actually is a case where we're going to need some substitution as we go through this integral process. So I'm just going to do a little side work over here. We need some substitution. Because right now, as that integrand stands, this thing, I don't know what gives that as a derivative. So let's try some substitution and see if that makes our lives a little bit easier. Okay, so this is a bit of a review of substitution. Remember, the first thing we do is we pick our u sub value, so the function of x we call u. And I'm going to choose the exponent to e. So u is going to be negative x cubed, which means du dx, the derivative of u with respect to x, is going to be negative 3x squared. Remember our third step of substitution, we solve what we got in 2 for the dx portion. So if I do that, I get dx equals negative du over 3x squared. And remember our fourth step, when we've got a definite integral, which we do here, we're going to perform the substitution on the limits of integration as well. So let's start with our 1. So if I apply my functions, my substitution u to 1, I get negative 1 cubed. That's negative 1. And if I apply this to r, I'm just plugging in an r into my u, so that's negative r cubed. Okay, so I've done my substitution, so let's see what that looks like. So this is going to be, still haven't done my limit. The limit as r goes to negative infinity of, okay, what happened with our substitution? So x squared, that stays the same. I have e to the u now. And my dx has become negative du over 3x squared. And my limits of integration, don't forget those as well. Now I'm integrating from negative r cubed to negative 1. Okay, so this x squared is going to cancel with this one, and that's going to leave me with, let's see, I have negative du over 3. That's negative 1/3. I'm going to go ahead and take that out of everything. So I'm going to put that right in the front here, even before my limit. And what's left in my integral here, or my integrand, I'm integrating from negative r cubed to negative 1. The only thing that's left in here is e to the u. So I've got negative 1/3 times the limit as r goes to negative infinity of, well, derivative of e to the u, or the integral of e to the u is just e to the u. So we're going to take that e to the u and evaluate it from negative r cubed to negative 1. Okay, so I'm still carting around that negative 1/3. I'm going to leave that there. This is the limit as r goes to negative infinity. And now, using the evaluation rule, or the evaluation theorem, this is e to the negative 1 minus e to the negative r cubed. Now this is where we have to be really, really careful. There's lots of negatives in here. There's lots of stuff going on. So it's a good idea to do this piece by piece just to make sure you know what's happening with all the negatives, what are all the values doing, that sort of thing. So let's see what we've got here. So I'm going to do this piece by piece. I'm going to think about what's going on as I take the limit. So e to the negative 1, that doesn't have an r in it, but I'm going to rewrite that as 1 over e, just to see what it looks like without that negative exponent. I think it's a little bit easier when you don't have negative exponents. Now, then I have negative or minus e to the negative r cubed. This looks a little rough, so let's do this very carefully. Let's consider negative r cubed. So what's r? R is going to negative infinity. So r is going to negative infinity. We are cubing that. And then we've got a negative in front of all that. So negative infinity cubed, the negative is still there, but it will cancel with this negative. So technically, e to the negative r cubed is the same thing as e to the infinity. And that's going to go to infinity. So again, negative r cubed, what's r going to? R is going to negative infinity. So I've got negative infinity cubed, that's still negative infinity, but I'm negating that. So those negatives are going to cancel each other out. Infinity cubed is still infinity, so I can rewrite that whole ugly thing as just e to the infinity, which goes to infinity. So I have some finite value minus something that's going to infinity here. But notice that I also have another negative sign out here with the negative 1/3. So this negative in the negative 1/3 is actually going to make this thing positive. Because if I distribute this negative 1/3 into here, I get negative something here minus negative something here. So that becomes a plus. And this 1/3, it's just a constant. It's not going to affect what's happening as r goes to negative infinity, because we have this term here, e. This thing's going to infinity. The 1/3's not going to influence anything. So I have some constant plus a term going to infinity. That's going to mean this entire thing is going to be going to positive infinity. In other words, what we just showed is this integral diverges. And actually, that's all the work we need to do for this example, because since we have one of these two integrals diverging, it automatically means that the original integral diverges as well. So I actually don't even have to look at this thing. I don't care, because I already know, based on what my results were here, that my original integral diverges. Okay, so I'm going to go ahead and write that down. So I'll say here, since this integral we were just working with, the integral from negative infinity to 1 of x squared times e to the negative x cubed diverges, we can conclude that the original integral we were looking at, so the integral from negative infinity to infinity of x squared times e to the negative x cubed, diverges as well. So since one of those pieces diverges, the original integral diverges as well. So there's two other things I want to mention here. These things called p-integrals and the comparison test, because both of these things can become very useful when you've got an integral that you want to evaluate that's maybe a little bit difficult, or with these p-integrals, it actually can act as a shortcut if you know what to look for. So let's start with these things called type 1 p-integrals. So if we're dealing with a type 1 improper integral, and our integrand, the function we're integrating, is of this particular form, 1 over x to the p, then we can use a shortcut to avoid having to evaluate the full integral every single time. So let's say our integral is of the form where we're integrating from a to infinity, 1 over x to the p. If p, our exponent, is greater than 1, the integral will converge. If that exponent p is less than or equal to 1, the integral will diverge. And so if we recognize that our integrand is of this form, we can actually use this p-integral information to determine if it diverges or converges without having to do any work. So let's actually go back to that example where we were looking at determining it, or in this case, we want to just determine if this integral of 1 over x converges or diverges when we're integrating from 1 to infinity. So notice, this thing is actually of this form. We're integrating from a constant to infinity, and technically our integrand is of the form 1 over x to the p. So this 1 over x is of the form 1 over x to the p, where p is just equal to 1, right? X to the 1 is the same thing as just x. So, because I have a p integral, my integrand is of this form, and I'm integrating from a constant to infinity, I can use this shortcut. I can see that p is less than or equal to 1, which allows me to immediately say this integral diverges. So since p is less than or equal to 1, the integral from 1 to infinity of 1 over x diverges. And we did this as an example up above, so let's see if we match what we got the long way. This was example 12.1.2. We could see that, yep, we're right. This does diverge. So a little bit of a shorter way of doing it if we recognize that this is a p integral. What about this one? So this is an integral of 1 over x to the 4/3. We're integrating from 1 to infinity, and we want to determine if this converges or diverges. So look at our integral. Limits of integration are from a constant to infinity, so that looks good. Now, let's consider our integrand. So our integrand is 1 over x to the 4/3. And this is of that p integral form, 1 over x to the p where in this case p equals 4/3. So what's our p? Where does it fall in our little shortcut here? Well, in this case, 4/3, that's greater than 1. So that automatically means that this integral is going to converge. So since p is greater than 1, the integral from 1 to infinity of 1 over x to the 4/3 converges. Now this shortcut's nice if you're just trying to determine when integrals converge or diverge. If you need to figure out what it's converging to, then you need to actually do some work, some actual calculation to figure out what this converges to. But if you're just trying to figure out if an integral diverges or converges, recognizing that p integral form, specifically of the integrand, is a really nice way of making that making a shortcut or using a shortcut if you're able to, when you're just trying to determine if a function converges or diverges. Okay, so that's convenient when you can recognize it. Of course, if you don't want to even worry about this and you're like, I just want to evaluate all integrals using the long way, that's perfectly fine. But this can be helpful just to cut things down a little bit in terms of workload. Now, the one other thing I want to talk about here before we start talking about type 2 improper integrals is I want to talk about this thing called the comparison test. So the comparison test is really useful when you're looking at a more complicated integral because it can be used in certain cases to determine if a complicated integral, one that's hard to evaluate, converges or diverges by comparing its behavior to the behavior of a quote-unquote easier integral, or an integral where we might know how it behaves. So let's say we have two functions, f of x and g of x, specifically in this relationship. So let's say f of x is at least the size of g of x, which is at least 0 for all x greater than a. The comparison test allows us to say specific things depending on the behavior of f of x and g of x. So first, let me just go ahead and draw a quick picture, a very generic picture of what's going on here. So let's say f of x, actually, I'll say this is point A. So for values of x greater than a, so for this part of the graph, we're saying that f of x is greater than g of x, meaning that this function f of x is always sitting on top or above this function g of x. So of course it doesn't have to look exactly like this, but that's the general relationship. The line, the curve of f of x is always above g of x on this interval. So the comparison test tells us that if f of x converges, or more specifically, the integral from a to infinity of f of x converges, then the integral over the same region for g of x must also converge. And visually, if we think about that, that makes sense, because what we're saying is if f of x converges, if that integral converges, it means that this area in red is finite. And we can see from the picture that the area beneath f of x is always going to be bigger than the area below g of x, because f of x is always above g of x. And so if this red area is finite, it has to mean that this green area is finite as well, which means g of x also the integral of g of x also converges. It also allows us to say another thing if the integral of g of x diverges. So if the integral from a to infinity of g of x diverges, then so does the same integral of f of x over that region. Which again, visually makes sense. If g of x, the integral of g of x diverges, it means that this area in blue is infinite. Because the area in blue is always going to be smaller than the area in red, because the area in red, of course, also includes everything above g of x, then if that blue area is infinite, then the red area must also be infinite, meaning that f of x must also, the integral of f of x must also diverge. So this can be useful, like I mentioned on this page, when you're trying to integrate or you're trying to determine if a more complicated looking integral converges or diverges. So let's consider this in this next example here. So here we want to determine if the integral of 1 over the square root of x cubed plus 5 on the region from 1 to infinity converges or diverges, and we're going to use the comparison test for this. Now, the first thing I want to do with this comparison test is I want an integrand that I can compare this to. And more importantly, what I want with this comparison integrand is I want something that I know information about its behavior. I know how it behaves on the region from 1 to infinity. So this is my original integrand. So 1 over the square root of x cubed plus 5. Now, how do I come up with a comparison integrand? What's a good thing to look for a comparison integrand? Again, what I want to pick for this comparison integrand is I want to pick it so that not only can I compare its behavior, or more specifically its size, to this thing, but I also want it to be something where I can very easily assess its behavior by integrating it from 1 to infinity. Now, I'm going to consider my denominator here. I'm going to say here, note, when x is large, I'll write it down here. This denominator of the square root of x cubed plus 5 is going to behave very similarly to just the square root of x cubed. Because as x gets bigger and bigger and bigger, which is fine to say or consider because we're looking at the integral from 1 to infinity, this square root of x cubed plus 5 is going to behave very similar to the square root of x cubed, which is the same thing, just to put it in terms of exponents, is the same thing as x to the 3/2. Now, why am I considering this? I'm considering this because for our comparison integrand, consider this original integrand, but with this as my denominator. So let's consider 1 over x to the 3/2. Our original integrand, or original improper integral, should behave similarly to the improper integral of this. So our original integral should behave like the integral from 1 to infinity of this comparison integrand. Now, why did I pick this as my comparison integrand? Well, of course, like I said up here, our original integral is very similar. Our original integrand is very similar to this integrand here. But also, if I take a look at this integrand, it's a p integral. I know how this behaves. So this 1 over x to the 3/2 is a p integral. Where my p is 3/2. And what does that allow me to say? Well, if p is 3/2, notice that's greater than 1. That tells me that this integral is going to converge over this region. So I can say the integral from 1 to infinity of 1 over x to 3/2 converges. Now, how do I relate this to the behavior of this? And again, more specifically, let's consider how this behaves compared to this. So I'll say here also, note that if I just compare 1 over the square root of x cubed plus 5 compared to 1 over square root of x cubed, what I'll notice is this thing is always going to be bigger than this. Or more specifically, I have this. Okay, so this denominator here is going to be bigger than this denominator here because we're adding 5 to it. And so this fraction here is always going to be smaller than this fraction here. And the reason I'm saying that is because this now relates my f and my g. My f is my 1 over x cubed. My 1 over the square root of x cubed. My g is less than or equal to that. I should say less than or equal to here if we're being technical. This is like my g. So this is like my f of x. This is like my g of x. We just said that f of x converges. And if f of x converges, g of x must also converge. So I'm going to say here, since we just showed by showing that we had a p integral, since this integral of 1 to infinity of 1 over square root of x cubed converges, then by the comparison test, the integral from 1 to infinity of 1 over the square root of x cubed plus 5 must also converge. So in other words, by the comparison test, we showed that this integral converges. We, of course, didn't show what it converges to. That's not really what we're interested in here. We just wanted to show that it does actually converge. So, like I usually do with these things that are a little bit more obscure, I like to put a visual with it. This is, of course, not something you'll be able to do on like the final exam or something. But if you're doing the comparison test on something like the web work assignment or a lab task, I always recommend graphing things if you can, because I think that makes things a little bit clearer. So in red, I have our comparison function, our comparison integrand, and in blue, I have our original integrand. So we just showed this, but we can see it here a little bit easier, I think, that notice it's very close, but if I zoom in, I can see that my comparison integrand is always above or greater than my blue one, my original one. So it's pretty close there, but it's always going to be above the blue one. We just showed, by virtue of the fact that our comparison integral is a p integral, the area beneath this red curve from, what was it, 1 to infinity? Yep. So this area defined from 1 to infinity under the red curve is finite. We said it converges, which means the area under the curve of the blue one is going to have to be, by nature, smaller because the blue curve is below the red curve. And so if the area beneath the red curve is finite, meaning the integral converges, the area under the blue curve must also be finite, meaning that the blue curve, or the blue integral, must also converge. Okay, so the red area here is finite, meaning that the blue area, because it's smaller, also has to be finite. In other words, because, move this to my other monitor here, because this thing converges, then this one must converge as well. Okay, so that's the comparison test. Sometimes it can be useful. Sometimes it just takes some practice as far as like picking that comparison integrand like we did here. Usually a p integrand is a good, or a p integral is a good comparison if you can make it, because those are ones that are easy to evaluate, as we saw up here, in terms of whether or not they converge and diverge. And that's really all we need in order to use the comparison test, is knowledge about whether a function converges or diverges. So we spent a lot of time talking about type 1 improper integrals because, as I mentioned, they're usually the more common ones that you run into. But of course, we have a whole other class called the type 2 improper integrals. And these are ones that are the ones with the discontinuous integrands. And more specifically, maybe in terms of terminology that we're a bit more familiar with, a type 2 improper integral is one where we've got a vertical asymptote occurring in our region of integration. And just like our type 1 improper integrals, there's basically three ways, or three types, three versions of the type 2 improper integral. One where the vertical asymptote occurs at A, one where the vertical asymptote occurs at B, so one of the two endpoints, or one where we have a vertical asymptote somewhere in between A and B, somewhere on the main range of our region of integration. So how do we deal with these? Well, let's go piece by piece. I'm going to call this version A. So let's say we're integrating f of x, and notice our limits of integration are back to being finite quantities. But now the issue is that we have a vertical asymptote that occurs at our lower limit of integration. Now, one nice thing about this type of improper integral is we approach it very similarly to the type 1 improper integrals, meaning we take that problem limit, so the one where the vertical asymptote is occurring, we replace it with a stand-in piece, so r, and then we take a limit. Now, rather than taking the limit as r goes to positive or negative infinity, what we do is we let r go back to the value it replaced. In this case, it's a finite value. And if it is our lower limit where this vertical asymptote is occurring, we take the limit as r goes to that lower limit from the right. So this is a one-sided limit. The limit as r goes to a from the right. And why does it have to be from the right? Well, this makes a little bit more sense visually. So let's say that this is a graph of our function f of x. And let's say, you could kind of see it on here, it's a little bit hard to see, but I've got a dotted line at a to indicate that this is where we have a vertical asymptote. So what we do is we pick a value of r somewhere between a and b. Let's say it's here. We take the integral, we find the integral from r to b, and then we let r approach a from the right, because we want r to be somewhere within that original region from a to b. Same idea if our upper limit of integration is the one that's giving us trouble. So let's say there's a vertical asymptote that occurs at b. Let's call this version b. We do the same sort of thing. We say, okay, b is giving us trouble here, so now let's replace b with a stand-in value r, and then let's take the limit as r goes to b from the left. Okay, so it's the same idea. It's just now, when we look at our graph of f of x, the vertical asymptote is occurring at b. So we pick a replacement for b. We call it r. Let's say it's here. Let me move it over a little bit. So now I can integrate from a to r using the evaluation theorem, no problem. And then at the very end, I take the limit as r goes to b from the left. Because again, what I want r to be something chosen as a placeholder between a and b. Now, finally, we have that type C that's a little bit more involved. Let's say that rather than a vertical asymptote occurring at one of the endpoints, we have a vertical asymptote that occurs at C, where C is some point between A and B. So on somewhere in our region of integration that's not one of the endpoints. So what we do, just like we did with our version C, so this is our version C of this type of improper integral, when we were doing this for these infinite limits, what we did is we broke the original integral up into a sum of two other integrals. We do the same thing, but instead of having to arbitrarily pick this a, what we do is we choose a as a placeholder for c, for that point where we have that vertical asymptote. So more specifically, plus a visual, if we're integrating from a to b, let's say c is the point where we have a vertical asymptote. So what we do is in our first limit of integration, or in our first integral, we integrate from a to r, where we're going to let r go to c from the left, and we add that to integral from r to b, where we eventually take the limit as r goes to c from the right. And just like we saw with this version for type 1 improper integrals, this original improper integral is going to converge if and only if both of the other integral limits exist and are finite. Otherwise, this diverges. So here's A, here's B, here's C. This is our vertical asymptote. And so now the idea is splitting this up somewhere where we can expand our region back till we hit C, so that we are able to deal with that vertical asymptote the same way we deal with it in versions A and versions B. It's just now it's in the middle of our region of integration instead of one of the endpoints. So let's do a couple examples with these. We won't go as in depth. We'll just do a couple and then talk about type 2p integrals. But let's go ahead and see what happens with this type of improper integral. So here we want to find the integral of 3 over x cubed as we integrate from 1 to 0, or we want to show that this diverges. Now if we just take a glimpse at this looks like a normal thing we could have done like back in the 11.1 notes with the evaluation theorem. We don't have infinite limits or anything like that, but notice that for our lower limit of integration here, my integrand is not defined. I can't have a 0 because that would give me a 0 on my denominator. And so what this would mean visually is we actually have a vertical asymptote at 0. So there's a vertical asymptote at x equals 0, making this a type 2 improper integral. So let's see how we handle this. All right, so I'm going to say 0 is the thing that's giving me trouble here, so I'm going to go ahead and replace 0 with r, which means at the end of this process, I'm going to have to take the limit as r goes to the value it replaced, and specifically as r goes to that value from the right. Now let's see if we can make this maybe a little bit easier to solve for that integrand. 3, that numerator is just a constant, so I'm going to go ahead and just take that out of everything, including the limit. So I'm going to rewrite this as 3 times the limit as r goes to 0 from the right. And we're integrating from r to 1. What I'm left with as my integrand is 1 over x cubed. I'm going to go ahead and rewrite that as x to the negative 3. Just to get rid of the fraction. This is going to be a little bit easier for us to solve. So let's go ahead and do that. So this is 3 times the limit as r goes to 0 from the right. Let's evaluate this integral. So I want to figure out what function gives me x to the negative 3 as a derivative. Now again, some of you might be able to do this in your head, especially by now since we've been doing this a lot. But of course, it's perfectly fine if you can't. We always have that nice little shortcut or a little cheat sheet where we have that formula specifically for this x to the n form. So n can be negative. So if you can't do this automatically in your head, that's perfectly fine. Here we're dealing with x to the negative 3. So we could use this general antiderivative formula, just like we've done a lot in class, to solve for the integral. Okay, so just for the sake of time, since this video is already running a little bit longer than the other ones, I'm just going to write down what this would be. You can try it with the shortcut if you want to. I don't know why I moved that. I was thinking that was a PDF, but it's my notes. So let me just put that back here. Sorry about that. Okay, so I'm just going to write down what this is. The function that gives me x to the negative 3 as a derivative is negative 1/2 x to the negative 2. And we're evaluating this from r to 1. Now, negative 1/2 is also just a constant, so I'm going to take that out as well. So I'm going to have 3 times negative 1/2 out in the front. Then I'm taking the limit as r goes to 0 from the right. And this is going to be, actually, let me rewrite this one more time. So if I take that negative 1/2 out to the front like I did here, I'm going to rewrite that remaining value, that x to the negative 2, as 1 over x squared. And we're evaluating that from r to 1. And again, I'm going to do that because that's going to make it a little bit easier for me to see the limit calculation. So let's keep going. So 3 times negative 1/2 is negative 3/2 times the limit as r goes to 0 from the right. Now I'm going to do my evaluation theorem here. This is going to be 1 over 1 squared minus 1 over r squared. So now here's where I take my limit. So 1 over 1 squared is just 1. This 1 over r squared, what's going on with this? Well, r is going to 0 from the right. So r is going to be something that's getting closer to 0 from the right. R squared is going to be always positive, but it's also going to be going to 0 from the right. So as this denominator goes to 0, this fraction is going to blow up to infinity. We saw that quite a few times when we were dealing with limits. So it looks like this might be negative infinity, but note I have a negative out here, so these things are going to cancel each other out, give me a plus. And so this thing is actually going to go to positive infinity. Or in other words, I can say here that this integral diverges. So again, I'm saying this goes to positive infinity because I have this minus this thing going to infinity, but I also have this negative sign out here. So if I were to distribute this negative, this thing would become a plus here in the middle, which would leave me with just a positive infinity as x, or as r got closer and closer and closer to 0. So again, like we've seen with a couple of these examples, be very careful with negative signs. Be very careful with what's going to a positive or negative infinity, and make sure you're canceling any negative signs with each other when that occurs. Let's look at one more example, and then we'll talk about p integrals for the type 2 improper integral. So here, we want to find the integral from -1 to 1 of 1 over x squared, or show that this diverges. So again, this looks like your nice normal integral that you might see with the 11.1 notes, but notice that my integrand is undefined at 0, and 0 is on my region of integration. So I'm going to have another vertical asymptote here at x equals 0. So there's a vertical asymptote at x equals 0. So the way that I'm going to handle this is I'm actually going to take my original integral and I'm going to split it into two. One of them, oops, I'll leave myself some space here. One of them, I'm going to integrate from -1 until I hit 0. Now 0 is the thing that causes trouble, so I'm actually going to replace 0 with r. And I'm going to eventually take the limit here as r goes to 0 from the left. And then I'm going to add to that the integral from r, the placeholder for 0, to 1. And I'm going to take the limit of this thing as r goes to 0 from the right. Now, just like we did when we did this for a case where both of our limits of integration were infinite, all I have to do here, maybe to cut down on some work, is just look at one of these two integrals at a time. So I'm going to go ahead and look at this one. If it converges, then I'll have to look at this one as well. If it diverges, as we talked about before, it means my original integral is going to diverge as well, and I just saved myself the work of having to look at both of these integrals. So let's look at this one first. Okay, so I'll keep writing this in blue. We're looking at the limit as r goes to 0 from the left of the integral from -1 to r of 1 over x squared. I'm going to rewrite that as x to the -2. Just again, because that makes it a little bit easier to take the integral. Okay, now again, you can use that cheat sheet if you want to for this. This is of the form x to the n, where n is -2. Again, for time's sake, for this video not to be too long, I'm just going to write down what this integral evaluates to. In other words, the function that gives us x to the -2 as a derivative is -x to the -1, and we're evaluating this from -1 to r. And I'm going to rewrite that into this -x to the -1 one more time. I'm going to write it as -1 over x. And we're evaluating from -1 to r. So we are taking the limit as r goes to 0 from the left. Now let's use the evaluation theorem. Evaluate this at r. That's going to be -1 over r minus -1 over -1. All right, now let's consider what's going on here. So this -1, again, be very careful. There's lots of negatives going on here. -1 over -1 is just 1. That's fine. What about -1 over r? So r is going to 0, but it's going to 0 from the left, meaning, just like we were doing when we were doing limits on their own, r is approaching 0 from a negative side, meaning that r is going to get smaller and smaller and smaller, but it's going to stay negative. So this fraction is going to be -1 over a small negative number. Now, if this was +1 over a small negative number, then this fraction would blow up to negative infinity, right? Because we have 1 over something that's getting bigger and bigger and bigger, but it's staying negative. So this whole thing would blow up to negative infinity. But our numerator is negative as well. So that means that this whole fraction is going to blow up, but the negative on the numerator is going to cancel with the negative on the denominator. And so this whole thing is going to blow up to positive infinity. And so I have positive infinity minus 1. The -1's not going to do anything as x gets bigger, or as r gets closer and closer to 0. So this thing is going to just go to positive infinity. Now, just like we did in that previous example where we were doing this splitting of this integral back on page 5, we noted that one of these two pieces was divergent. And so, just like we did in this example, we can say in our current example, since we just showed that this one integral diverges, we can conclude that the original integral that we're interested in diverges as well. So I'm going to say here, since the integral from -1 to r of 1 over x squared diverges, then the original integral of -1 to 1 of 1 over x squared diverges as well. So once again, we actually don't have to look at that second integral. We don't even have to worry about this thing because we just don't have to. We've already showed that one of these two pieces diverges, which means the original integral diverges as well. If we had shown that this thing converges, so let's say instead of infinity, this was like, I don't know, 4, then we would have to go and look at this integral. If it converged to 4 as well, then we would say the original integral converges. Or if it converged to something else, then it would be this thing, 4, plus whatever this thing converges to. And that would give us the end result. But since we showed that this first one is divergent, that means that the original integral is divergent as well. Now, one last thing here with a very short little example are the type 2 p integrals. So another nice thing about these improper integrals is we have this p integral form for both. So if we're dealing with a type 2 improper integral, and our integrand is of that 1 over x to the p form, that same thing we saw with the type 1, then we can use yet another shortcut to avoid having to evaluate the full integral if we're just curious about whether the integral converges or diverges. So let's suppose that we're integrating from 0 to a of 1 over x to the p. Now, by virtue of the p integral integrand form, this is going to be undefined at 0. So we have a vertical asymptote at 0. But we can use our shortcut to determine if we have divergence or convergence. So if p, the exponent, is greater than or equal to 1, we can say that the integral diverges. If p is less than 1, then we say the integral converges for this type of p integral. So let's just do one quick example here. Let's determine if the integral of 1 over x from 0 to 1 converges or diverges. So first thing we want to do is we want to recognize, is this a type 2 improper integral? It looks like it, because it looks like at 0 we have a vertical asymptote, because 1 over x, when x is 0, we have the 1 over 0 form. So we do have a type 2 improper integral. And if we consider our integrand 1 over x, it is of the 1 over x to the p form. So our integrand of 1 over x is of the form 1 over x to the p, where p equals 1. Now we can use our shortcut. P is greater than or equal to 1, so this integral, by default, diverges. So since our p, our exponent, is at least 1, the integral from 0 to 1 of 1 over x diverges. So again, if you're able to recognize that you have a p integral for either your type 1 or type 2 improper integrals, it can be a nice shortcut if you're really just interested in determining if the integral converges or if it diverges.